the main intuition or like message that I want to like convey is that if you work with quantum information, the best way is to keep it as much quantum as you can and process it natively as much as you can. And for this, to explain how these quantum linear algebra techniques help with this, I will explain first a little bit a bird's eye view on quantum linear algebra. So I guess everyone is familiar with the HHL algorithm in the audience. Just let me recall it. We want to solve some large system of linear equations, AX equals B, and we want to leverage that a quantum computer can nicely work with an exponential size matrix. And if we are given the vector B as a quantum state, then using the HHL algorithm, we can prepare a solution that's again a quantum state, which is proportional to the solution vector X, which is A inverse B. And later, this algorithm inspired many other algorithms and has been improved in various ways. And I just wanted to sketch like my view on this algorithm is that we have an input matrix A, and in some way we make this matrix accessible to a quantum computer in a way that implement basically all the assumptions boil down to the ability to implement a quantum circuit where the top left corner of this unitary is the matrix itself A, which is also called the block encoding of this matrix A. And then what we want to do is, given this matrix A, we want to transform it via some function f and get a new block encoding and apply that to some specific quantum state. And in the HHL algorithm, this function is just a 1 over x function, which inverts the matrix. And you can use a singular value transformation to apply this function to this matrix, and then ultimately this leads to HHL algorithm. But if you use different function, then you can also solve different tasks using this scheme in general. So there are more examples that fit into this little framework. For example, optimal Hamiltonian simulation of quantum walks are nice examples of which can also be understood via this block encoding language. Also fixed point, oblivious amplification, and various versions of those. Then HHL, regression problems, semi-definite and linear program solvers, and other machine learning type algorithms. And what I will talk about this talk more is this quantum information task that include distribution testing, including density operators, fidelity and entropy estimation, and implementing Petz recovery channels and these kind of tasks. And so a few more words on block encodings, because this is where I will, this is what I will explain how this block encoding framework can be used for somehow accessing and processing quantum information in a way natively. So as I said earlier, block encoding is just a way to represent large matrices in a quantum computer efficiently in terms of a unitary matrix, which is implemented by efficient quantum circuit. And in principle, for any matrix A, which has operator norm at most 1, we can find the unitary which block encodes it. But the key here is to find a unitary which is also efficiently implementable, and that's the challenge. And one can efficiently construct such block encodings under various conditions. For example, a trivial condition is if the matrix A itself is efficiently implementable unitary, of course, we can represent it in a quantum computer very easily. Well, this is a trivial example, but later we can do modifications of these matrices, linear algebra. So actually, this is a useful building block, although it's very trivial. Then what is used in the HHL algorithm, the original one by Harrow, Hasidin, and Lloyd, is if you have a sparse matrix with efficiently computable elements, then you can also represent this matrix as a quantum circuit. And then a different model, which is usually used in quantum machine learning, is that you have access to a matrix which is stored in a clever data structure in a quantum accessible RAM, a QRAM. And now there are more physics motivated examples where you can have nice block encodings. And this is what we will use mostly in this talk, is that if you have a density operator rho and you are given a unitary that prepares its purification, then you can get a block encoding of rho itself quite easily. And more generally, if you have a POVM operator M, where we can sample from the random variable trace rho M, sort of implementing this measurement, then we can turn this measurement implementation to a block encoding of this POVM operator M itself. And so you can have block encoding of various matrices coming from any of these 5 or even more possibilities. Once you have these efficient block encodings, you can start working with them and you can combine them in various ways. You can take convex combinations of these matrices, also called linear combination of unitaries trick. And if you have block encodings of A and B, then you can implement block encoding of A times B or A tensor times B. So these are operations that are easy to implement on a quantum circuit level if you have the block encodings to begin with for A and B or AJs. Okay, so now these are just the basic tools that we can use, and now how to apply it to different problems. So here I just wanted to spend a few more minutes on this density operator block encoding. So suppose that you have G, which is unitary matrix that prepares the purification on some ancilla system qubits, such that if you trace out the ancilla qubits of this pure state, then you get density operator rho. So this is the input model that you have such a unitary. Then it's known that if you extend basically your system with another copy of this system register, then you apply this G tensor identity on the system, a swap of the system registers, and again a G tensor identity, just with G dagger, then this is a block encoding of rho. And this is actually fairly simple to show using a Schmidt decomposition for this density operator. And while I don't really have time to go through this computation, but really it's just a few lines of trivial computation, one can see that it is indeed a block encoding of the density operator rho. I don't expect you to see all these steps. I just wanted to say that it's an easy computation, really. And so basically, if we can prepare the quantum state rho, then by applying this preparation unitary and its inverse together with a swap gate, we get the block encoding of rho exactly. And this is what we want to use in several applications. And so another important ingredient is a quantum singular transformation, which tells us how we can transform a block encoded matrix. And it can be formulated the following way. So suppose that we have a polynomial which maps -1, 1, the interval -1, 1 to -1, 1, and it's a degree D odd polynomial map, meaning that only the odd degree terms have a non-zero coefficient in the polynomial. Then the following is true if you have a circuit which is a block encoding of the matrix A, where A has this singular value decomposition sigma I, Wi, Vi, then you can turn it into a new block encoding where the singular values of A get transformed by this polynomial while the singular vectors stay the same. That's why it's called singular value transformation. And this is just by applying some angles, basically a single qubit rotation on a specific qubit, and these angles can be efficiently computed. And the ultimate circuit is something like this. So one needs to repeatedly apply U and its inverse, and in between these applications, just apply a generalized Toffoli gate on the ancilla qubits representing the block encoding, and then a single qubit rotations with these angles that can be computed from the polynomial efficiently. And so the number of times you need to apply U or U inverse is D, the degree of this polynomial. And similar result holds for even polynomials. And this whole thing simplifies for Hermitian matrices where P just acts on the eigenvalues. So you can just say that this polynomial is directly applied to the Hermitian matrix as a matrix function in the usual sense. Okay, so this is how you can transform a single block encoding efficiently. And I just want to showcase this again by the favorite example of the HH algorithm and show how to directly implement the pseudo-inverse of this matrix A. So suppose that A has this singular value decomposition W sigma V. Then the pseudo-inverse by definition is A plus, which is you reverse the order of V and W and invert the non-zero diagonal entries of sigma. And then the zero diagonal entries just stay zero. So by definition, that is the pseudo-inverse. And well, note that one way to reverse the order of W and V is just instead of working with A, working with A dagger. So that's at least does the job for reversing the order of V and W. And now, if you work with A dagger instead of A, the only thing that remains is to invert the singular values in this diagonal operator sigma. And well, then it's what you need to do is just find a polynomial approximation of the 1 over x function and apply it to this sigma matrix using quantum singular transformation. Now, the problem is that this 1 over x function is a not very nice function. It diverges around 0. So in particular, it cannot be approximated by bounded polynomials that are required. However, if you know that you have a region around the origin where you have no non-zero singular values, then you can just find a polynomial that approximates this 1 over x function well outside this interval. And this interval is essentially determined by the condition number of this matrix. Then you just find such a polynomial, apply it, and you get your algorithm. And it turns out that the degree of a polynomial that does a good job at approximating this 1 over x function outside this small interval is kappa log 1 over epsilon, where epsilon is how precise you want to be outside this forbidden interval. And then basically this tells you what is the complexity of the entire algorithm. Well, in this simple case, actually, due to the subnormalizations appearing, you will get a quadratic dependence on kappa, which can be improved either by something like variable time amplification, or there are different algorithms that also improve the kappa dependence. Okay, so just to abstract out what was happening here, the main idea was to find a nice matrix function and implement it by quantum singular transformation. And this applies to different other problems as well. For example, in Hamiltonian simulation, it suffices to find good approximations of sine of tx, cosine tx, combine that, and we get e to the itx, which is just a Hamiltonian simulation problem. Now, in place of x, just plug in the Hamiltonian itself, and we get Hamiltonian simulation. Or you can, instead of real-time evolution, you can just apply the same trick to imaginary time evolution, which then basically gives efficient algorithms to give sampling. And then again, just the function is you replace e to the itx by e to the minus beta x. That is the function you approximate by polynomials. And also, it turns out that Grover search, amplitude identification, and quantum walks, they are all special cases of this singular transformation. And there, the functions that appear are just Chebyshev polynomials. And for an n-step Grover search or quantum walk, the nth Chebyshev polynomial of the first kind is what appears. And all the analysis can be done just by this understanding. And variants of these are like, for amplitude amplification, a problem is that you can see these functions, these Chebyshev functions are highly oscillatory. And so if the amplitude to begin with is maybe was a bit larger than expected, it can happen that you over amplify the amplitude and ultimately end up with a very small amplitude. This is undesirable. And you can just turn this algorithm to a better algorithm where you only need a lower bound on the initial amplitude or success probability. And that you get by just finding a good polynomial approximation of a first step function, essentially. And this is what is called a fixed point amplitude amplification in the literature. All right. And yeah, some question that I often get is that what is the gate complexity of this algorithm? And well, basically, it's just implementing the block encoding itself, and you repeat it d times. So it's really just from the block encoding plus a few elementary gates times the degree of the polynomial, which depends on your function that you need to approximate. So this framework is not only like easy to work with on a high level, it also gives rise to algorithms which are actually gate efficient. So that is a nice thing in this. Yes, and now a few more words on this fixed point amplitude amplification. So the basic problem is that we are given some quantum algorithm, unitary U basically, that prepares with some probability p a good state and marks it, say, with a 0 and selected with saying that it's the good state, and with some if it doesn't succeed, then it produces some bad state. But we focus on the good state, and we just want to prepare this psi good. That's the goal. And now how we apply single rate transformation here, that we realize that basically the top the first half of the first column of U, that is essentially just the quantum state psi good, and the singular value of this small matrix is just square root p. So essentially this is again a single rate transformation problem, and you can just find this approximate threshold polynomial that I sketched on the previous slide. And you can actually generalize this problem to the following, that suppose that you have a matrix A, again, which has singular decomposition W sigma V, and suppose you have this matrix, you want to implement a unitary, which is W V dagger. In the previous case, that would be just the unitary that maps the 0 initial state to psi good. And you can implement that approximately using the above method. But you can also ask for this problem when this matrix A does not only consist of a single column, like in amplitude amplification, but this is actually a matrix which has larger dimensions. And this is the problem of singular vector transformation, which is just the above problem, but we need to be careful about difficulties arising from small single values, because like small amplitude, so we can only guarantee this procedure to work above some threshold. And one other way to state this is that we have this block encoding of A, which has some left and right singular values, vectors psi I. And now we want to construct a unitary that transforms one copy of a quantum state, which is a superposition of alpha I psi I, to a different state where we replace this right singular vectors psi i's with left singular values pi i's, but keep the same amplitudes. It's another way of saying that we want to implement this W V dagger. And while we can do it for all those singular vectors for which the corresponding singular value is at least, say, delta, and again, the degree necessary for this is something like 1 over delta. So the lower bound on this singular values, 1 over that, times logarithmic in the desired precision. Okay, so we will use this. That is why I meant to a little bit more details on this application in the following. Now I turn to explain 3 problems in information processing where you can natively apply these techniques. So the first one is application to distribution testing, where I just described for a basic classical algorithm and then how to improve it quantumly. So one approach is that you first have an unknown distribution P. You first sample an I with probability Pi. Then you estimate by repeated sampling this probability Pi, and then you output some function of this estimate that you can compute. For example, if you wanted to compute the entropy of a distribution, then you would output the logarithm of this estimate that you get. And by repeating the entire process so far, you can get an estimate of the expectation value of this f of Pi, which would be, for example, the von Neumann entropy. This is just the logarithm. F is the logarithm that we choose. And the quantum improvement that is possible upon this is, which was observed by Bravi, Harrow, and Hasadin in 2009, is that you can use amplitude estimation to estimate this probability Pi in the second step, Pi tilde, basically quadratically better than classically by amplitude estimation. And further improvement, and so for this, what you need to assume, Bravi, Harrow, Hasadin assumes that you have a unitary which somehow prepares a sample from this distribution. So it maps, say, the O0 state to something which with square root Pi, I, and then there's also a phi I register, which is some unknown ancilla state. But you can just read out the last register, and if you measure the last register of the state, then you get with probability Pi a sample I. So this is like a quantum version of sampling, but a coherent one. Under this assumption, you can apply amplitude estimation. And the realization is that we can achieve further improvement by implementing a block encoding of something which have square root Pi's in the singular values. And that way we can basically skip this intermediate estimation step and somehow directly estimate the expectation value. Because in this master algorithm above, you have twice this estimation step, and that introduces extra overheads that are really unnecessary. So here, what essentially happens is that you keep this information about the distribution quantum and only convert it to a numerical estimate at the very end. And this is the general theme that I wanted to sketch here. And a nice way about viewing this early algorithm via this lens and using this block encoding, which have singular values, square root Pi's, is that it's not only that we improve on Bravi, Harrow, and Hasadin results, but also because we somehow treated quantum information in a coherent way, the results and the techniques directly generalized to also density operators. So we get new algorithms for computing the same functions, just now for density operators. So, for example, we move from von Neumann entropy estimation, from Shannon entropy estimation, which is for classical distributions, to von Neumann entropy, which is a generalization to quantum states. And for this, what we require is a purified access, so that we assume that we can prepare a purification of the density operator as described before. Yes. And while in this context, somehow it introduces extra difficulties that we have density operators. So the whole process works as before for density operators, but somehow we pick up a square root and overhead that seems to be necessary actually in this situation. And yeah, so here just again.
So this is because you start from maximally mixed state?
Well, on a technical level, yes. On an intuitive level, I would say the reason is that whereas, so in the classical case, you know that at least you know the right singular vectors. The right singular vectors are somehow these I registers. So somehow know the basis in which your density operator is diagonal, and that is just given by the computational basis states. And for that reason, some quantum circuits simplify. And in the density operator case, when you don't know the diagonalizing basis, then somehow you need to like implicitly search for it. And in technical terms, indeed, you kind of need a maximally entangled state in the process. Yes. So just schematically, you had the unitary that prepares that samples, and then you transform it to a block encoding where single values are just square roots of the probabilities. You apply quantum singular transformation, and then you get diagonal metricity with square root of fp, and you just apply this operator to a single sample that you take, and then now you have this sum over I, square root pi, square root fpi, and so on. And if you would measure this state and condition on the first qubit being 0, then you get something which is proportional to the expectation value, sum over pi f of pi, and that is just the expectation value of f of p. And whatever is your function, logarithm, or what else, you get your final estimate. And using this machinery, we could improve on various testing and estimation problems, for example, L1 closeness testing, L2 closeness testing, or entropy estimation. And here is in the first row, you can see the complexity of this problem when you have only samples classically. And then the coherent is the second line, which was when you can sample in a quantum way that I described what was the previous best algorithm for this. And using these techniques that I described in a paper with Tongyang Li, we have the so far best complexities for these problems. And you get improvements mainly in epsilon and sometimes new algorithms. And as I said, as a bonus, these results automatically extend to quantum distributions with a square root and increasing the complexity. And so if you now study the problem of L1 closeness testing, L2 testing, entropy estimation for density operators, if you have only access to copies of the quantum states, then the first row tells you the complexities that are known, and the bottom row is this model when you can prepare purifications of the quantum states. And this is actually a model that were not really considered for these problems before. But now we know how to exploit this more strong input model. And these are the complexities that you get. Okay, another problem where you can apply this philosophy is, for example, fidelity estimation. And here the problem is that suppose that we can prepare purifications of rho and sigma, and we want to estimate with, say, additive precision epsilon, the fidelity of these two quantum states, which is defined in the usual way. And the problem is in general hard. So and it seems to require a polynomial time in terms of the rank of the minimum rank of rho and sigma. So we will have algorithms that depend on the rank and that are applicable to low rank quantum states, when at least one of the quantum states has low rank. And here the idea would be is that to use this latter definition of these fidelities, that it's just the one norm, the shortened one norm of square root rho, square root sigma. And that you can state as the trace of square root rho square root sigma, and times this singular vector transformation of this square root sigma square root rho. So basically applying these unitaries in this singular vector decomposition, and that basically transforms this one norm to a trace, and the trace is something that we can usually estimate in quantum algorithms, so that's a much nicer formalization. And further trick is that what we can usually do in quantum algorithms is that we take a quantum state and apply an operator and then compute expectation values. And so this square root rho we turn into rho times 1 over square root rho, and then rho is a quantum state, and we imagine as the latter part as an observable, and we can then measure that using amplitude estimation or something like that. So this is the general trick. And then, yeah, here we use this single vector transformation as an important subroutine in this formula. And then, again, the main part of the algorithm is just implementing the block encoding of this operator, while we need to subnormalize with something like this, 1 over square root rho times square root sigma, and then single vector transformation of this square root sigma square root rho. And then in the technical level, we use a Hadamard test to get the final expectation value out, and then repeat using amplitude estimation. And this shall soon appear on arXiv if you do all this analysis carefully. And then with Alexander Poremba, we showed that the overall complexity of estimating the fidelity to epsilon precision is something like rank to the power 2.5 over epsilon to the 5, and times this T rho and T sigma is just the time complexity of preparing the purifications rho and sigma. And again, you can see the power of using your quantum information natively, because other algorithms that were having these additional inner estimation steps and so on that can be ultimately like skipped to the very end. Those algorithms, the prior best algorithm that used such overheads had a much higher complexity. So we could dramatically improve it using these techniques. And a bonus is that although I described all of this in this model when we have already access to purifications and unitaries preferring purifications of these density operators, this algorithm can be directly converted to an algorithm which only assumes samples, so it only assumes having access to copies of rho and sigma. And this is done by basically density matrix exponentiation. Basically, by density matrix exponentiation, one can turn this sampling access to block encodings again, and then just apply the previous scheme. And this, again, gives us a new algorithm, the best so far for this incoherent access when we have only copies. And there the complexity is something like rank to the 5.5 over epsilon to 12, still better than the prior best algorithm with a stronger input assumption. And well, I don't have much time for it, but we can also, in a different paper, we show how to implement Petz recovery maps using the same machinery. And the general idea is, again, to pick a definition of this Petz recovery channel, which is suitable for these techniques, and somehow break down the implementation of this Petz recovery channel to a number of steps that can individually be implemented by quantum single vector transformation. And some important realization, which was not so clear before this picture of quantum linear algebra cleaned up, that somehow you can amplify this whole procedure, which initially seemed to have some very small success probability, to have success probability arbitrarily close to 1 by oblivious amplitude amplification. And that's, again, a particular case of single vector transformation. And then we show this in a paper with Seth Lloyd, Iman Marivian, Iho Ikvik, and Mark Wilde in 2020. Unfortunately, I don't have time to go into details here. But I have time for last summary slide, which just kind of summarizes the various applications and how these speedups arise from this machinery. And well, I can say that we can say that exponential speedups are possible due to the dimensionality of the Hilbert space, and that is something that is present, for example, in Hamiltonian simulation or HHL itself. And a different sort of exponential speedup compared to prior art, at least, it comes from precise polynomial approximations. For example, the exponentially improved arrow dependence of the HHL algorithm falls into this category. And then there are quadratic improvements possible due to, for example, due to the fact that singular values that appear in these matrices are generally the square roots of the probabilities of the classical algorithms. Rover search basically can be viewed as having the quadratic speedup due to this fact. And also single values are somehow easier to distinguish than just probabilities, and amplitude estimation exploits this. And in quantum walks, somewhat more niche phenomenon occurs. Somehow close to one singular values are more flexible, and that gives rise to a quadratic speedup that can be exploited in other places like almost like frustration-free Hamiltonians and so on. And so there are many more applications of this of these techniques that are getting increasingly more standard. And I hope that it makes sense how these information tasks are a good candidate for further speedups possible. Thank you.